Okay, so hello everyone, and today we are going to talk about the multivariate distribution, which is a discussion from the last time. Okay, so in this video, we are going to talk about the last two topics, which are the conditional distribution and the discussion about the histogram. Okay, so let's get started. So, what is conditional distribution? Suppose we have n variables, let's say x1 up to xn, with the continuous joint distribution for this one, okay? And let f0 denotes the marginal joint PDF of k, which is less than n. For all values of x1 up to xk such that f0 of this one is greater than 0. So this one is make sure that we do not divide it by 0, okay? Because the formula is here. So if we talk about the conditional distribution, this one must be greater than 0. But in the last time, when we talked about, let's say, the product rule, okay? Let's say the product rule. About the product, let's say multiply this one with this one, okay? And if we talk about the law of total probability, if we discuss about these two concepts, we do not require this condition, okay? But we require this condition because we want this to be the denominator. And we define this one to be conditional variable for the convenience, okay? So the order doesn't matter. The conditional PDF of this one given x1 up to xk is this one, the above one, okay? The above one is the joint distribution, okay? The joint distribution. And we divided by what? We divided by the condition that we impose on. The condition that we impose on is the marginal, okay? That is, we flatten out from n variables to how many variables? To k variables, okay? So this one is the marginal. Marginal is the concept of flattening out. So this formula is very similar to what we have seen in previous videos, okay? So I hope that you're familiar with this. Okay, so let's get started with the first example. Suppose that C is a random variable for which the PDF F0, okay? So for F0, that is this one, okay? So given C greater than 0, we have other two random variables that depend on C, okay? That depend on C. And x1 and x2 are IID. That is, they are independent from one another. So we want to find the probability of this one. So the first question, when we see the question like this, is that what we wish we knew. Okay? What we wish we knew. We wish we knew what? We wish we know the variable C, right? Because if we know C is treated as if it was the constant. Okay? So what we wish we know, the answer is the random variable called C. That is what? That is, we have to use the law of total probability. That is, we have this one, okay? The integration of the probability x1 plus x2 less than 4, and given C is equal to any C and D C here. This one is what we are going to find. Okay, so let's see the solution. So because we know that they are IID, what can we conclude? We can conclude that we can multiply these two together to get the joint probability. Let's say, remember, if we have marginal, can we always get the joint? The answer is No, except one special case. What is that special case? Is independence. It doesn't have to be IID, okay? Because IID is identical and independent. So with only this condition, we can get the joint distribution, okay? The joint distribution. But we still have C. What we wish we knew is C. So we use the concept of product rule, okay? So this one here, we use the concept of product rule. With this one, we can multiply F0 of C with this joint distribution. What we get is this one, okay? So next, we could find F12. F12, that is, we are going to flatten out because we have the joint with how many variables? With 3 variables, but we have to flatten out to have only 2 variables. The only way to get rid of C is integration with respect to DC, and we will get this one. So for some of you, this integration may not seem a bit obvious, okay? Because we have C here and we have C there also. So the technique that we are going to use here is the bypass integration, okay? So you have to take bypass integration from 2 times, okay? From 2 times. The first time is flattening out C squared up until C, and from C up until the constant, okay? And that way we can use the formula to integrate only the function of E, which is EC, okay? Because we treat x1 and x2 as if a constant. So the probability that x1 plus x2 is less than 4, we can get something like this, okay? So we draw the diagram, okay? x1, x4, x2. And we have this one 4, this one 4, and this one. So we're going to get only this area. How are we going to get this area? The answer is that because C first, C1 and C2 must be greater than 0, so we have this one. The area is this one and this one, the dot, okay? So if we integrate with respect to x1 first, okay? So how does x1 span? x1 spans from 0, okay? From 0 up until what? Up until 4 minus what? Minus x2, okay? 4 minus x2. And then integration with x2, okay? Integration with x2. Oh, sorry. So we have to integrate by x1 first, right? So x1 is this axis, okay? So this one is 0. This one is x2, right? So that means 4 minus x2. This one is the first integration, but you can take the integration in any direction first. It is fine. And in this direction, we integration from 0 to 4, and we get 4 over 9 as the answer. So next, Bayes theorem, okay? Bayes theorem. T2 of C given Y. So I use bordered letter. That means it is a vector. It doesn't mean that's only one C. It can be 1, 2, or 3, or any finite number of variables here. So, straightforward formula. Treat it as if it is one variable case. So, T2 of C given Y. If we find that it is easy to find Y given C, we find that first times by F2 of the vector C and divided by F1 of vector Y. And F1 of vector Y, it is that we are going to flatten out, because notice this one. This one is, let's say, the edge of vector Y and vector C. right? This one is this vector. So we flattening out the C by integrating, okay, by integrating with respect to DC. And if it is conditionally independent, okay, conditionally independent, that is independent given C, like what we saw in the last example. So we can multiply this X together, but because it is conditional, so we are conditional on the vector C. That means what? That means we are going to multiply G of any X, each X given by the whole vector C. Okay, so the concept is very similar to what we have seen before. The second example, suppose that there are 3 more observations, x3, x4, x5. Also, each of xi are conditional ID, denote y, denote w, and what we want to find is d2 of c given y and w. So what does it mean? What does it mean? It means that because what we are given is, let's say, y, w given c. This one is easy, but this one is difficult. Okay, from the easy one to the difficult one in this case, that's why we're going to use the Bayes theorem. It might seem too straightforward, but when we look at the practice problems in, let's say, the next few videos, I am not going to tell you in advance what techniques we are going to cover, because you have to discover that by yourself. Okay? So, and we are going to go through a number of problems in those videos also. Okay, the solution. As they are what? They are conditionally independent. Okay, so we get this one, we get this one. And because we get this one, we can calculate this one first. And then we can calculate this one. It is conditional because we are given W. We are given W using Bayes rule, we can find this one. We are given W, we can find this one. And we can use this one, okay? So this one, G2 of C, given vector Y and vector W is what? It is the vector Y, okay, F1 of Y and C given W and, okay, let's say F3, F1, F2 of C given W. But we can simplify this further. Okay, we can simplify this further. That is, we can find what? We can find F1 of Y given W, and we can find, let's say, H of C given what? F of, oh, we have this one already, right? Okay, I see. So we can use these 3 expressions, okay? We can use this 3 expression, G1, F2, and F1 to substitute in these expressions, okay? Because we can, let's say, multiply this one with this one, okay? So this one, it can be decomposed to G1 times F2, okay, G1 times F2. Oh, it must be Y, right? It must be Y. So this one must be Y, yeah. must be y, because we have this one and we got to get rid of y. So this one must be f1 also. This one must be f1 also. Okay, so we can substitute this two expression into this formula to get this number. Okay, because this one is, we expanded this one, right? And we get c given w and y given c. So we get this expression and we get the below expression to get it of y. Okay, correct. So let's go to the final topic of this series, the histogram. What is the histogram? Histogram, let's say, looks a bit like this. It is a model of the probability distribution. Okay, so let's say this one is x, this one may be the frequency or the percentages, and we have maybe something like this. So the histogram is a key in order to model the probability distribution, and we will see this again in chapter 5. Okay, in chapter 5, and we're going to see this again in maybe if you study about the mathematical statistics. Okay, which may be the next course maybe. So x1 until xn is the collection of number or line into value. That means we have to define the minimum and maximum first. And we divided into what? Into k equal length. Okay, k equal length b minus a over k. And for this interval, we count. Okay, we count how many of these number fall in this category. Okay. And then we draw the two-dimensional diagram, and for each subinterval, draw a rectangular bar that is corresponding to C, right? Corresponding to C over R. So R here is the hyperparameter to what? To govern what will be the height. Okay. So if you want the height to be the percentages, okay. If you want the height to be percentages, the R should be n, right? N over what? Over 100. So that if we find Ci over R, it's gonna be Ci over n times 100. It's gonna be percentages. Okay, so sometimes we do not want only the frequency, but we want something like the proportion, so that we can see what the shape actually looks like. Okay, and this one with this topic. So the use of histogram is to approximate the probability distribution that we have seen before, and we're going to see this again in chapter 5 when we talk about the frequently used, the discrete distribution and continuous distribution. And what's next? We have finished almost all concepts already, but except one final topic in next video, which is if we have the PDF of random variable, let's say the random variable x, let's say x according to any distribution, but if we have fx, let's say the most basic one is a linear function ax times b. What is its distribution? And stay tuned for the next 2 lessons. Okay, so see ya.